Hello, everyone, and thanks for tuning in. This is a recording of an informal presentation that I did for the Archean Fault Rocks Workshop, which was a precursory small field trip for the 6th International Archean Symposium held here in Fremantle and Perth. Um, so the presentation is about in situ stress in the Yilgarn terrain and mine site seismicity. And in a sense, I was a guest at the conference, which was mostly about exploration and structural geology. Um, But the reason I'm doing this kind of presentation is for the last couple of years, I've been involved in sort of the transition between structural geology and geotechnical engineering, and have been seen a lot of spots where there's been mine site seismicity. So this is partly just a presentation about that, what I've discovered during that time, and how I've made sense of the difference in terminology and made sense of the way that structural geologists might contribute to the solution of the problem of underground seismicity. So there's basically three parts. I've got a quick review stuff at the beginning, and then part two is general about the in situ stress in the Yilgarn, some information about stress measurements and West Australia mining stresses. And then part three is a specific example of how underground mining changes the state of stress around the underground excavations, and then uh, some preliminary thoughts and constraints on underground seismicity, the sizing and risk of small earthquakes, and a quick mention of earthquake mitigation or risk mitigation. The quick takeaways from the presentation is the Yilgarn in situ stress is horizontal compression, or you could call it reverse faulting. So this is a generalization, but it does seem to hold true pretty much across the entire craton. Second, the faults are weak. They're not sources of stress, and that's probably a misleading way to think about them. So think of faults as weak rather than stress sources. Underground mining causes huge changes to the in situ stress. So having worked in, say, oil and gas, the biggest thing there is to depressurize the reservoirs or drop the fluid pressure. In underground mining, those excavations underground, like the stopes, the drives, the declines, those things make huge changes to the in situ stress. Generally, I've found it useful to think of mining as an unloading process. So although people say, well, the mining causes higher stresses, it does in a sense, but really what's happening is stress is being redistributed. And in general, the rock is losing strain energy as you're doing those excavations. So it is formally an unloading process. I'm going to try to convince you that magnitude 2 to 3 earthquakes might be the largest likely induced seismic event in the Yilgarn Craton. We might have bigger ones, and particularly the southwest part of the Yilgarn Craton is now under study as an active area, or one of the most active areas in Australia for small earthquakes. So then, of course, the big question is, as mining goes deeper, we know the geotechnical problems get worse, including the seismicity. So the question on everybody's mind is, how deep can we go? And that's in a sense, the reason to try to figure this out. If we can mine to, say, 2,000 meters instead of only 1,500 to 1,600, that's a big plus for the industry and a big plus for the economy. So part one, basic stress and strain terminology. Um, So stress and strain observations and humanity. So remember, stress is a tensor quantity. So is strain. So we're used to life in a fluid, and in a fluid there's one pressure only. There's no shear strain in the air or in water. So if you're a scuba diver, that's the diagram all the way over on the right, you know that every 10 meters of water is worth another atmosphere. And the stresses underground, they're not just a pressure, but they are a stress, and they're hundreds of atmospheres. So a human stress magnitude that might help you just get the idea about the magnitude is under boots. So my weight's somewhere around 100 kilos, rounding off. I won't say exactly what it is. 220 pounds. So then you can figure out the area of your boot soles in terms of square inches or meters squared. And then you can easily arrive at a vertical stress estimate under your boots of somewhere around 2.5 psi, which is 1 atmosphere is about 14 and a half. So under your boots is about a sixth of an atmosphere, and hopefully that puts it a little bit in context, the stresses that are underground. So I have a few editorial comments about stress and strain. So remember, as geologists, we can observe strain. Um, in fact, as humans, we can observe strain. It's pretty hard to observe stress because we're not used to living in a solid. We can't feel the stresses. We do have to do a fairly extensive inference process to come up with estimates of the stress. Can be measured, but only with instruments. Whereas finite strain, we can see that happen. We can see the changes in shape of things. And I do like to keep the terms straight. So pressure, compression, tension, shear stress, and normal stress are the right words to use for stress. And then things like convergence, contraction, shortening, extension, lengthening, and stretching are the right things to use for strain. So one of the common ones that just to keep in mind is if you're a structural geologist and you see folding and faulting, you see thrust faults or whatever, it's tempting to say, well, you've got compression. Well, you probably do have compression, but remember what you actually can see is the shortening or the contraction. And it helps to keep that in mind and use the right terminology for what you can actually see. Some more terms that can be confusing, particularly between, say, mining and geotechnical and structural geology and to some degree oil and gas. So breakouts are a well-known phenomenon in oil and gas, and you can see them in boreholes, underground wells. And typically what happens is because of the stress concentration around a borehole, you'll get compressive failure in the little green areas shown on the diagram on the left. And then you can also get tensile fractures or fracking on the area there. And the relation between the principal stresses is shown there. So the directions, the orientations of the breakout give you information about the orientations of the stress. Particularly easy to interpret in a vertical wellbore, but you can do it with an inclined one as well. We tend to observe the breakout width. The mining industry has some spectacular examples of this because we do have, in a sense, what you could think of as very big diameter boreholes. So the classic ones would be raised bores and ventilation and services tunnels that are 1, 2, maybe even 3 meters in diameter, and they're done with a raised bore machine or a large, a very large drill bit. And you can observe these, say, even with a drone or just looking down a large thing, or sometimes they're used as escapeways, and so then there's a ladder in there, and you can just make direct observations. Another thing that happens in